A magnetic field is the magnetic effect of electric currents in magnetic materials. The magnetic field at any given point is specified by both a direction and a magnitude. As such, it is a vector field. The term is used for two distinct but closely related fields denoted by the symbols B and H, where H is measured in units of amperes per meter in the SI. B is measured in teslas and newtons per meter per ampere in the SI. B is most commonly defined in terms of the Lorentz force it exerts on moving electric charges. Magnetic fields can be produced by moving electric charges and the intrinsic magnetic moments of elementary particles associated with a fundamental quantum property, their spin. In special relativity, electric and magnetic fields are two interrelated aspects of a single object, called the electromagnetic tensor. The split of this tensor into electric and magnetic fields depends on the relative velocity of the observer and charge. In quantum physics, the electromagnetic field is quantized and electromagnetic interactions result from the exchange of photons. In everyday life, magnetic fields are most often encountered as a force created by permanent magnets, which pull on ferromagnetic materials such as iron, cobalt, or nickel, and attract or repel other magnets. Magnetic fields are widely used throughout modern technology, particularly in electrical engineering and electromechanics. The Earth produces its own magnetic field, which is important in navigation, and it shields the Earth's atmosphere from solar wind. Rotating magnetic fields are used in both electric motors and generators. Magnetic forces give information about the charge carriers in a material through the Hall effect. The interaction of magnetic fields in electric devices such as transformers is studied in the discipline of magnetic circuits. History. Although magnets and magnetism were known much earlier, the study of magnetic fields began in 1269 when French scholar Petrus Peregrinus de Maricourt mapped out the magnetic field on the surface of a spherical magnet using iron needles. Noting that the resulting field lines crossed at 2 points, he named those points poles in analogy to Earth's poles. He also clearly articulated the principle that magnets always have both the north and south pole, no matter how finely one slices them. Almost 3 centuries later, William Gilbert of Colchester replicated Petrus Peregrinus' work and was the first to state explicitly that Earth is a magnet. Published in 1600, Gilbert's work, De Magneta, helped to establish magnetism as a science. In 1750, John Michell stated that magnetic poles attract and repel in accordance with an inverse square law. Charles Augustin de Coulomb experimentally verified this in 1785 and stated explicitly that the north and south poles cannot be separated. Building on this force between poles, Siméon Denis Poisson created the first successful model of the magnetic field, which he presented in 1824. In this model, a magnetic H field is produced by magnetic poles and magnetism is due to small pairs of north-south magnetic poles. 3 discoveries challenged this foundation of magnetism, though. First, in 1819, Hans Christian Ørsted discovered that an electric current generates a magnetic field encircling it. Then in 1820, André-Marie Ampère showed that parallel wires having currents in the same direction attract one another. Finally, Jean-Baptiste Biot and Félix Savart discovered the Biot-Savart law in 1820, which correctly predicts the magnetic field around any current-carrying wire. Extending these experiments, Ampère published his own successful model of magnetism in 1825. In it, he showed the equivalence of electrical currents to magnets and proposed that magnetism is due to perpetually flowing loops of current instead of the dipoles of magnetic charge in Poisson's model. This has the additional benefit of explaining why magnetic charge cannot be isolated. Further, Ampère derived both Ampère's force law describing the force between two currents and Ampère's law, which, like the Biot-Savart law, correctly described the magnetic field generated by a steady current. Also in this work, Ampere introduced the term electrodynamics to describe the relationship between electricity and magnetism. In 1831, Michael Faraday discovered electromagnetic induction when he found that a changing magnetic field generates an encircling electric field. He described this phenomenon in what is known as Faraday's law of induction. Later, Franz Ernst Neumann proved that, for a moving conductor in a magnetic field, induction is a consequence of Ampere's force law. In the process he introduced the magnetic vector potential, which was later shown to be equivalent to the underlying mechanism proposed by Faraday. In 1850, Lord Kelvin, then known as William Thomson, distinguished between two magnetic fields now denoted H and B. The former applied to Poisson's model and the latter to Ampere's model and induction. Further, he derived how H and B relate to each other. The reason H and B are used for the two magnetic fields has been a source of some debate among science historians. Most agree that Kelvin avoided m to prevent confusion with the SI fundamental unit of length, the meter, abbreviated m. Others believe the choices were purely random. Between 1861 and 1865, James Clerk Maxwell developed and published Maxwell's equations, which explained and united all of classical electricity and magnetism. The first set of these equations was published in a paper entitled On Physical Lines of Force in 1861. These equations were valid although incomplete. Maxwell completed his set of equations in his later 1865 paper A Dynamical Theory of the Electromagnetic Field and demonstrated the fact that light is an electromagnetic wave. Heinrich Hertz experimentally confirmed this fact in 1887. The 20th century extended electrodynamics to include relativity and quantum mechanics. Albert Einstein, in his paper of 1905 that established relativity, showed that both the electric and magnetic fields are part of the same phenomena viewed from different reference frames. Finally, the emergent field of quantum mechanics was merged with electrodynamics to form quantum electrodynamics. Definitions, units, and measurement. The B field, the magnetic field, can be defined in several equivalent ways based on the effects it has on its environment. Often the magnetic field is defined by the force it exerts on a moving charged particle. It is known from experiments in electrostatics that a particle of charge q in an electric field E experiences a force F equals QE. However, in other situations, such as when a charged particle moves in the vicinity of a current-carrying wire, the force also depends on the velocity of that particle. Fortunately, the velocity-dependent portion can be separated out such that the force on the particle satisfies the Lorentz force law. Here v is the particle's velocity and times denotes the cross product. The vector B is termed the magnetic field, and it is defined as the vector field necessary to make the Lorentz force law correctly describe the motion of a charged particle. This definition allows the determination of B in the following way. He command, measure the direction and magnitude of the vector B at such and such a place, calls for the following operations. Take a particle of known charge Q. Measure the force on Q at rest, to determine E. Then, measure the force on the particle when its velocity is v. Repeat with v in some other direction. Now find AB that makes the Lorentz force law fit all these results, that is the magnetic field at the place in question. Alternatively, the magnetic field can be defined in terms of the torque it produces on a magnetic dipole. The H field in addition to B, there is a quantity H which is also sometimes called the magnetic field. In a vacuum, B and H are proportional to each other, with the multiplicative constant depending on the physical units. Inside a material they are different. The term magnetic field is historically reserved for H while using other terms for B. Informally, though, and formally for some recent textbooks mostly in physics, the term magnetic field is used to describe B as well as or in place of H. There are many alternative names for both. units in SI units. B is measured in Teslas and correspondingly phi B is measured in Webers, so that a flux density of 1 Weber per square meter is 1 Tesla. The SI unit of Tesla is equivalent to, in Gaussian CGS units, B is measured in Gauss. The H field is measured in amperes per meter in SI units, and in Ørsted in CGS units. Measurement. The precision attained for a magnetic field measurement for gravity probe experiment is 5 attoslas. The largest magnetic field produced in a laboratory is 2.8 kT. The magnetic field of some astronomical objects such as magnetas are much higher. Magnetas range from 0.1 to 100 GT. See orders of magnitude. Devices used to measure the local magnetic field are called magnetometers. Important classes of magnetometers include using a rotating coil, Hall effect magnetometers, NMR magnetometers, squid magnetometers, and flux gate magnetometers. The magnetic fields of distant astronomical objects are measured through their effects on local charged particles. For instance, electrons spiraling around a field line produce synchrotron radiation that is detectable in radio waves. Magnetic field lines. Mapping the magnetic field of an object is simple in principle. First, measure the strength and direction of the magnetic field at a large number of locations. Then, mark each location with an arrow pointing in the direction of the local magnetic field with its magnitude proportional to the strength of the magnetic field. An alternative method to map the magnetic field is to connect the arrows to form magnetic field lines. The direction of the magnetic field at any point is parallel to the direction of nearby field lines, and the local density of field lines can be made proportional to its strength. Magnetic field lines are like the contour lines on a topographic map in that they represent something continuous, and a different mapping scale would show more or fewer lines. An advantage of using magnetic field lines as a representation is that many laws of magnetism can be stated completely and concisely using simple concepts such as the number of field lines through a surface. These concepts can be quickly translated to their mathematical form. For example, the number of field lines through a given surface is the surface integral of the magnetic field. Various phenomena have the effect of displaying magnetic field lines as though the field lines are physical phenomena. For example, iron filings placed in a magnetic field line up to form lines that correspond to field lines. Magnetic fields lines are also visually displayed in polar auroras, in which plasma particle dipole interactions create visible streaks of light that line up with the local direction of Earth's magnetic field. Field lines can be used as a qualitative tool to visualize magnetic forces. In ferromagnetic substances like iron and in plasmas, magnetic forces can be understood by imagining that the field lines exert a tension along their length, and a pressure perpendicular to their length on neighboring field lines. Unlike poles of magnets attract because they are linked by many field lines, like poles repel because their field lines do not meet, but run parallel, pushing on each other. The rigorous form of this concept is the electromagnetic stress-energy tensor.